So next, I would like to put a necessary and sufficient condition for a rectangular matrix to have a right inverse. But before that, I will show a simpler theorem provided in the textbook. Okay, so now consider linear system AX equal to B. If A has a right inverse, then this linear system has at least one solution. X equal to B. We call right inverse to B. Then, sorry. So if A has a right inverse B, then this linear system has at least one solution. And B, the right inverse times B. And the proof is very direct. Alright, so we just check with X equal to B, we have, okay, so AX equal to A, B. Okay? And this is AB, B, by associativity of metric multiplication. And this is the identity. Okay, so we have checked that this is indeed a solution. Okay. So we have one solution. That's easy. Right. Now, the second supplementary theorem say that M times N matrix, okay, is a right inverse if and only the columns of A span M. Okay. So in A we have n columns, and each column is m dimension. Okay. So the step is say that matrix A has a right inverse if only the n columns of A span the whole m dimensional Euclidean space. Right? Now the forward part. Right? So we want to show that the column space span the Rn. Right? So we want to show every vector in Rn. So every vector. So let B in Rn. So we want to show every vector in Rn is in the span of the columns of it. Inside is in the column space of it. So to show that B is in the span of where we want up to the end R. Okay, so we want to show that B is in the span of the set of all columns of A. We should find x1, x2, up to xn, such that x1a 1 plus x2 a2 plus plus xn an equal to b. Alright, so we have to find coefficients x1, x2 up to xn such that b can be expressed as a linear combination of the column vectors. Okay, and this is equivalent to finding a solution of the linear system. Okay. So let's find it. But such a linear system, because A has right inverse, so the linear system has at least one solution. Now, since A is a right inverse, at least one solution exists, right, by the previous theorem. Thus, B is in the span of A1, A2, up to An. Okay, so now we know that B is in span. But the span is A1, so this implies that Rm is contained in the span 1 but span A1, A2 up to is a subspace of Rm. So we have Rm is equal to the span. Okay, so we finish the forward part. Any questions? It's just a routine, right? Because we use the same argument several times. Any questions? Right, so if no questions, then we go to the reverse part. The reverse part says that the column space of A is equal to the n dimension within space. And from that, we have right inverse. Right, and similarly, we will do it directly. We will construct the right inverse. All right. So now for each standard, the plot, the idea, will be similar to the idea I gave to you when I proved that if the kernel of a rectangular matrix A is trivial, then this matrix A has a left inverse. So it's similar, but let me proceed. Okay, so for each standard unit vector EI, okay, so EI they are BI1, BI2 up to BIN such that BI1 A1 plus BI2 A2 plus plus BIN AN equal to BI. Since span of A1 Right, so every vector in Rn, especially in particular the standard unit vector, is the linear combination of the columns of it. Okay, and so we can find coefficient BI1, BI2, BIN, such as EI is just expressed as linear combination, like this one. Is that okay? All right. So so that we know A, BI1, BI2 up to BIN. This is just A. Right, so the linear combination can be written as the product of a matrix A and the column vector, which is equal to BI. Okay? So A multiplied with this column vector formed by the coefficients here is equal to BI. Okay, and then we put them together. A, BI1, BI2. Oh. So we call this as B I. Okay. So we have A, BI equal to BI. So now A, B1, B2 up to Bn is equal to E1, E2 up to Bn. And we let this is matrix B, and of course this is just equal to identity. Okay? Oh, M. Sorry. the dimension of A is m times n, and this is n times n. So we have AB equal to the identity. So B is a right inverse of A. Okay, and we have that. So the right inverse can be constructed by the coefficients here. So as you can see, I use the similar argument over and over again, right? Very similar pattern of arguments, just manipulation of matrix multiplications. For example, here, express linear combination as a matrix multiplication. And sometimes, for the matrix multiplication, can kill the linear combination. So they are just the same thing with different formulation. And then we just put together everything here. Maybe you will see right here. Okay. Because we have m standard unit vectors in Rn. Okay, so we have m equation like this one, and we put them together. And this one is identity, and this comes to a matrix. Okay, so it's just like a doing things from some basic block to build a bigger one. What? Any questions? We will finish the proof. Alright, so up to now, they are all about the immutability of rectangular matrices, right? Rectangular, not necessarily square. Okay, so a rectangular matrix may have a right inverse or may have a left inverse. Now we go back to this definition has been mentioned earlier. So a square matrix A is invertible if there exists an n times n matrix B such that A times B equal to B times A equal to the identity. It's about invertibility of of a square matrix. So the square matrix should have a right inverse and a left inverse, and this left and right inverse are the same. And we have shown before, actually chapter 1, if an n times m matrix A is an inverse, then there is only one such an inverse, saying that inverse is unique. Okay, so we proved that before. The inverse of an invertible m times m matrix A is both left inverse and right inverse of A. Okay, so from the definition, so the inverse of an invertible matrix is both a left and a right inverse. Okay, so question. For a square matrix A, is it possible that 1 CA equal to, so it has a right inverse, it has a left inverse and right inverse, and then C now equal to B. The equation is like this one. Because we learned, because rectangular square matrix is also a special type of rectangular matrix. Okay, and so that we are asking that this A, for example, has a left inverse and also has a right inverse, but left inverse and right inverse are different. Can that situation possible? All right, so the next theorem in the textbook answer such a question. So if A and B are square matrices such that, so A and B are square matrices has the same dimension, such that BA is equal to the identity. If this is a condition that say that B is a left inverse of A, then B is also a right inverse of A. So it's very strong. So if you, for a square matrix, if you find a left inverse, say B, then this left inverse must be also a right inverse. And then because it is also a right inverse and right and left inverse, so by the definition, this B is the inverse of A, and A is invertible. So can you see the effectiveness of this theorem? To show a matrix, a square matrix, not the square matrix A, to be invertible, you just show that it has a left inverse or it has a right inverse. For example, in here, A is a right inverse of B, right? And then A becomes to a left inverse of B. Okay? So remark. If a square matrix has a left inverse, then it is invertible. So if a square matrix A, I'm sorry. Then left. Alright, so if a square matrix, important thing, square matrix, not just rectangular, should be square. Alright, so if square matrix A is a left inverse B, then A is invertible and B is the inverse of A. Second. Similarly, if a square matrix A is a right inverse, B, then A is invertible, and the B is the inverse of A. Okay. So these two remarks are immediate consequences of the theorem. And remember, in the first chapter, we are solving when we try to find an inverse of a square matrix, we usually to solve AX. And we asking if we can find a solution, right? So this is M. So this is an unknown M by M matrix. So to find a right inverse is equivalent to solve this matrix equation. Okay? And we can do so by using to solve the augmented matrix, right? We apply elementary operations to this augmented matrix to see if it is consistent or inconsistent. If consistent means we can solve it, we can find a solution. Then this solution must be a right inverse. Okay. And by this theorem, this right inverse implies that A is invertible, and the right inverse is exactly the inverse of A. So we finish our job. Okay. So in chapter 1, we learned the technique to solve this. But we just say that the solution is a possible candidate in the chapter 1 because we don't know the theorem, right? So we find a matrix, and then we check whether B is the left inverse, okay, to satisfy the definition. And of course, you are always successful. Why? Because of the theory. You never fail. Never. Because once you find a right inverse, this right inverse must be a left inverse. And so this matrix must be the inverse of it. Never fail. Okay, that is in the situation of chapter 1. Okay, in the situation of chapter 1. Without the theorem, you can solve m linear systems simultaneously. And if you are successful, then you have a right inverse. And then you check this right inverse whether it is also a left inverse. And you always successful. If you cannot find any right inverse, then A is not invertible. At this moment, okay, you know that if you can't, then it's not invertible. Sure. Okay. All right. So we go to the proof. Okay, so what we know is that BA is the identity. Alright, so since BA is the identity matrix, i.e. B is a left inverse of A. I happen. So if there's only condition for a matrix, because a square matrix is also a rectangular matrix. Now we prove in theorem 3.2.8 that a rectangular matrix has a left inverse if and only the kernel of A is trivial. So this is it has left inverse, so that the kernel okay? And when the kernel is 0, which implies that so that each column of the reduced row echelon form U of A has a pivot. Because when you solve the okay, so U is the reduced echelon form of A. This corresponding to homogeneous linear system. Okay, kernel of A says that when you solve the homogeneous linear system, there is only one solution, which is 0. Now, by row operations, elementary row operation, you get to the reduced echelon function. If there is a column has no pivot, remember, column with no pivot, the corresponding variable can be set to be free. Right? Remember that? When we have free variable, we have infinitely many solutions. Not only the trivial solution. So every variable must be dependent, not free. That means that every column should have a pivot. Because every column has a pivot will be dependent. Only a column without pivot, the corresponding value will become pivot. Okay, so that you right, every column of U must have a pivot. And then so what is U? U is M times M is a square matrix because A is square. So the reduced echelon form is also a square. Every column has a pivot. Means every row has a pivot. So the only possible U is that U is equal to the identity. It should be 1, 0, 0, 1. Because every column has a pivot, every row has a pivot, and above, below pivot must be all zeros. Remember the echelon form, right? The reduced echelon form, when you have a pivot, the entries above the pivot, below the pivot must be zeros, must be cancelled, right? That is the rule for the reduced echelon form. Okay, and so finally U should be like this one. There is no other choice. And so that is the identity. So again, we push back to Gauss-Jordan elimination, right? Every time, if you can, you just push to the reduced echelon, right? So U is this one. But and what is the consequences? Okay, so now to solve an M times M matrix, and to solve a matrix in AX equal to the identity. Because we want to find a right inverse, as I just indicate here. So this is M times M, and I have an unknown matrix to find. So X should be, if I can solve it, right? Then X should be the right inverse. Okay, so to solve the associated augmented matrix Alright, it's now A, I, okay, so this is M times M, M times M. By elementary machine, now you have U and the W. Yes. Okay. So U is the reduced partial form of A. Goes here. And this U, what is the U? Identity. Okay. So this is identity here. And because it's identity, the system of linear equations, they are consistent. Right? Because every law has a pivot. Since every row of U is a pivot, U, W is consistent. Right? And then X equal to W is a solution. I.e., we have AW equal to the identity. So now we find a right inverse. Okay, so let's review here. We start with a left inverse. Okay, so we start with a left inverse here. Okay, and from that, we know the kernel of A is trivial. Alright? And so that every column of the reduced differential form of A is a pivot. And because that A is square, so the reduced differential form U is also square, and so that U must be the identity. So anyway, we have that. And we try to find the right inverse. Okay, and we find that when we do the elementary operation on the associated augmented matrix, when we find that the system of linear equations are consistent. Okay, so they're consistent. And then this is indeed the W is the solution. Alright, so we find a right inverse. Alright? And then now B is B is B. Again, we use the similar argument before. B is equal to B. Look, I want to find the W is equal to B. Right? Now, so B is equal to B multiplied with identity, but identity just established that AW is identity. And the BA, because B is left-hander, so this is equal to W. Now B is equal to W. So that we have A, B equal to that. So we have that. So the crucial point is just to find a right inverse. Questions? Alright, so there are several companion theorems. For a square matrix of dimension m, if AB equal to AC equal to the identity matrix, then B equal to C. Okay, now why? AB, when, as I said, when AB is I, then B must be the inverse of A, because AB equal to identity means A is invertible. So B must be the inverse of A. AC equal to I means that C is the inverse of A. And the inverse is unique, so B equal to C. Finish. Okay? So think about the theorem here. So once we know that if we have BA here, so we know that B is the inverse of A and A is the inverse of B. And so we have a corollary. Sometimes is that EA equal to CA, you will understand. Then B equal to C. This is just, if we have two left inverses, then they must be the same, because they are the same as the inverse of A. And the 7, for an M times M matrix, if CA is equal to the identity matrix is also equal to AB, then C will be. So the theorem answers our question. If A has a left inverse called C, and the B has a right inverse called B, then C will be, of course, because they are the inverse of A. So no other choices. Okay, so let's a break for 10 minutes. So that a non-invertible matrix is also called singular matrix. Okay, so they are different terms but have the same meaning. So non-singular matrix means invertible matrix. Alright, so non-invertible. Alright. It's called singular. Okay, so quite often you will encounter textbook saying single matrices. So single matrices means non-invertible matrices. Okay, so the theorem 3.2.9 plus 10 together is important. So it has a name called invertible matrix theorem. Right now, so for a square matrix, A, the following statement, and the following statements are equivalent. Alright, so I will state along actually 15 statements. A is invertible. Right? A is invertible. For each B in Rm, the linear system Ax equal to B is a solution. A comment, and then there is only one solution. For each, it's very important. A is invertible if and only for each B in Rm, the linear system has a solution. So this is saying that the column space of A is just Rm. But 2 and 3 actually the same meaning. So that each, why? Because that if A is non-invertible, it is possible that we can solve a linear system for some spatial B. For example, if B is 0, right? If B is 0, then we have trivial solution, right? Always. So the crucial part is that for each, every, that is very important. For every B, the linear system has a solution. So that this means that the column space of A is equal to the Rm. Okay? So they have the same similarity. And we know 2 means that the second statement means that A, because it has at least one solution, means that A has a right inverse. Right? This is from the necessary sufficient condition for a rectangular matrix to have a right inverse. The column space is equal to Rm. for kernel of A is trivial. Right? So kernel of A is trivial means that the matrix A has a left inverse. Once a square matrix has a left inverse, then it is invertible. Okay. Fifth one. Every column of A is a pivot. Alright? Every column of A has a pivot. Means that the reduced echelon form of A is a pivot in every column. Because what? Because the kernel of A is trivial. Okay. So that the variable corresponding to each column is dependent. There is no free variable. 6. Every row of A, every column. Of A, every row of A has a pivot. Why? Because A is a square. Every column has a pivot means that the rank of A is saying that the rank of A is M. Okay? One, two, three, four, five, six, seven. Okay, 8. The transpose of A is invertible. Because every row of A has a pivot. Now, row of A becomes column of transpose of A. And because every row has a pivot, so every column of A transpose has a pivot. Right? And so that A transpose is invertible. 9. A is row equivalent to the identity. Alright, so it means that identity matrix is the reduced echelon form of A. So every invertible matrix will goes to only one possible reduced echelon form, which is just the identity matrix. They are even remaining invertible M by M matrix. But when you apply the elementary law operations, doing the Gauss-Jordan elimination, the destination will go to the same matrix, identity matrix. Every, no exception. Okay? Every invertible matrix will go to this one. 10. The set of all columns of A is linearly independent. This is the consequence of that. The kernel of A is trivial. Okay, so the set of all columns of A is linearly independent. This is 10, right? We have 5 more. 11. The set of all rows of A is linearly independent. because A transpose, because there is no here, the reduced low echelon form is identity, so there is no zero rows in the reduced echelon form, low echelon form. Okay, so we have a theorem saying that if the row echelon form of A has no zero rows, then that all the set of all rows is linearly independent. Right. Well, it's the same. Okay. I'm sorry. The columns of A span M. Actually, this is the same as this one. Okay. Yeah, I can eliminate this, but 15 is a good number than 14. So this is L1. The linear transformation P from Rm goes to Rm such that the x goes to Ax. Okay. So the linear transformation, because the matrix A can establish a linear transformation, okay, by sending a column vector in Im to a column vector in Im. So this linear transformation is injective. Means one to one. Okay. Because the kernel of A is trivial. So a linear transformation is injective if only if the kernel of the linear of P is trivial. But the kernel of P is just the kernel of A. Right? So that so this one, the 4, is equivalent to the 13th statement. Now the 14th, the linear transformation P from Rm goes to Rm such that x goes to Ax is surjective. It means until. Why? Because the column space is equal to Rm. Once equal to Rm, then say that it's surjective. Last one. The linear transformation is bijective. Means 1 to 1 and until. Of course. On 15, you have 15 statements, they are all equal. They are equivalent to each other. It's a kind of summary, right? From chapter 1 to chapter 3. A very good endpoint for the first midterm examination. Okay? Any questions? So you have to know the reason why these 15 statements are equivalent to each other. Okay, you have to identify at home as an exercise to prepare for the first midterm. If we fully understand why they are equivalent to each other, then I think you are well prepared for the examination. Otherwise, you have risk. Okay. Okay, so now we have more time, so I will start an interesting subject in linear algebra called determinant. All right, determinant. 4.1 introduction. Okay, I will give a different approach from the textbook to deal with determinants. Okay. And then I will show that my approach is equivalent to the approach in the textbook after we have some background in chapter 5, the next chapter. Okay, so we need some concept in the future. And the reason why I would like to introduce my approach is because my approach is much more simpler. Okay? Well, the author of text may have different arguments, say that they have a simpler approach than me. Well, I will not argue with them. By the way, I don't know. I'm not familiar with them at all, actually. All right, so now let n times n, okay, be the set of all n times n square matrices. So it's the set of all n times n square matrices. And we know that this set n times n is a vector space. Okay, so it's a vector space. For example, the addition, just the matrix addition. So when you add the two square n times n square matrices, you get an n times n square matrix, of course. Scale multiplication, if a matrix is scale multiplied with a constant, then every component, every entry in the matrix will be multiplied with the same constant. Okay, so again, it's an n times n matrix. So the closure properties are obvious for the vector addition and scale multiplication. And we use the associative law, we use commutativity law of addition, and we use the distributive law from the beginning of the class, right? So that we exploit that this set is vector space from the beginning of this class. Okay. Now we will fix n. Okay. Right. So we fix the dimension of these square matrices. So we'll consider n times n square matrices. Okay. Now, a determinant function called DET is a function the vector space of all n times n square matrices to the set of real numbers. So DET is from n goes to R. Right, so determinant function is that we will assign a value to each square matrix. And this value will be called the determinant of the matrix. Okay. Alright. So, but it's not just a function. It satisfies three axes. Such that it's a property 1. Okay, maybe I will say x is 1. We call identity xm. That the SM1 says that the determinant of the identity, so a matrix goes to DET A. Okay? So the mapping is that for every matrix A, will go to the determinant A. So we assign the determinant, the value for identity matrix to be 1. Okay. So the assignment should be to have this property xm2 we call linearity on the first row. Okay. In reality, on the first row says that the determinant of a matrix and the first row okay? So if the first row of the matrix can be written as a linear combination of two row vectors, U1 and U1. Oh, I see. I think I use R. It's better. One prime. Maybe I use and R2 N. Okay. R is one more better. Then it comes to the determinant of 1, 2 up to N plus beta determinant of 1 prime 2 up to N. Okay, so we want the function is linear on the first row, SM3, called the row exchange. That the determinant of row 1, row I, row J, row N, is the minus of the determinant if we exchange these two rows. Okay, so this here is the ith row. Here is the J0. Now the I0 becomes 2. So that we put the original J0 to the I0 of the new matrix. Okay. Once we have done this, then the value of the determinant will change the sign. So we put minus here. Okay, so any function if it exists, okay? Any function if it exists. If it exists, then satisfying these three axioms will be called a determinant function, et. So let's see special cases. Example, n equal to 2. Okay? So now we want to know the A, B, C, D. Can we construct a function satisfying the three? So we are saying that we define that AD minus BC. So AD here, that's AD minus BC. Define the determinant function here. Okay, so it's a function, right? From 2 by 2 make the M 2 by 2 up to R. Okay, and we have to check. So we just define axiom 1. So 1, okay, determinant 1, 0, 0, 1. We want to see if the determinant of the 2 by 2 identity matrix is equal to 1. So this is 1, 1 minus 0. Okay, so it's good. So x1 is fulfilled. Okay, second. Determinants, maybe I need more space. Okay, so we have alpha A plus beta A prime, alpha B plus beta B prime, and CD. Note that alpha A B plus beta A prime B prime is equal to alpha A plus beta A prime alpha B plus beta B prime. So that the first row is a linear combination of two rows. Okay. All right, and definitions here, right? So we have alpha A plus beta A prime times B minus alpha B plus beta B prime times C. Right? By definition. And this is alpha AB minus alpha BC plus beta A prime D minus b from c. And we take out alpha. And what is that? This is determinant of A, B, C plus beta, determinant of A prime, B prime, C. Okay, so xm 2 is full field. Third one, determinant A, B, C, D. By definition is AB minus BC. So this is become 2BC minus AB. And this is by definition determinant of CD and AB. So xm 3 is 4 here. Okay, so conclusion. So we conclude that DEP defined in above is a determinant function. Okay, so it's a determinant function. So we start with a definition. Right? So this is, we know that the determinants of a 2 by 2 matrix here. We learned that from junior high school, right? I think so. So, so after checking, we know that by this definition, the DET is a determinant function. But we don't know whether this is the unique one, right? Can we have other determinant function for 2 by 2 matrices? That's the question, right? So, even though we establish a determinant function, but can we have other different determinant function for 2 by 2 matrices? Even more serious, do we have a determinant function, at least one determinant function for arbitrary unbiased matrices? We can? Okay. If we do, the next question is unique. So we always have the existence and uniqueness problem. Okay. And also we have to build a way to compute the determinant, right? An efficient way to compute determinants in the development. So this is all what we want to solve in this chapter. So let me give a remark here. Our goal actually. So we will show, right? So we will show that there is one and only one determinant function on the vector space. That's for each n greater than equal to 1 determinant function is unique. But before we are able to do so, we have a lot of work to do. All right? And so, so we next develop a series of properties for a determinant function. DET if exists. Alright, so we assume that we have one. Okay, so if we have one, then what are crucial properties of such a determinant function? Okay, so we will see the consequences of the three axioms. What axioms? Three axioms tell us. Okay, and from that we dig out. We will know the inside of a determinant function, so that we are able to prove that there is one and only one determinant function. Okay, and I have to relate. Oh, by the way, I have indicated because sometimes you have the example. It's the theorem 4.1.3. Okay. This the proof I gave here actually is a proof for theorem 4.1.3. Okay. And alright. A remark I have to make here. First one, axiom 1 is a special case of property 4 times 1 times 1. Right. Axiom 3 is just theorem 4.1.1. Okay, so basically I use the this is for you to compare with the textbook. Okay, so basically the textbook use three basic properties. Alright, so axiom 1 is just a special case of the property number 1. So property number 1 is more advanced. Okay, so it and so we just use a special case, just a very little information. This is give you a big information, a big property. And also I select the result in theorem 4.11 as axiom 3. Okay? So just for you to compare. Right. Alright. So that I'll do that. This is the beginning. 4.1.8. We call equal rows. Alright, so I will use the name of a property because that it's hard for you to memorize the serial numbers, right? It's very hard. So that it's about equal rows. Equal rows, what is that? The determinant. If I have if I have a matrix such that two rows are equal, okay, so this is the ith row, this is the jth row, all right, and these two rows are equal, they are R here, okay, then the determinant is equal to 0. So it's called the equal row property. The proof is simple, just by using axiom number 3. Why? Well, the determinant is equal to the minus the determinant. Why we can change the minus sign? Because we exchange the ith row and the jth row, right? But when we exchange them, we keep the same matrix. So we exchange. When we exchange the ith row and the jth row, then we get the same matrix, but we have to change the sign by axiom 3. And a value is equal to its negative value. There is only one solution. What is that? 0. Right? So we have that. We have this one. So whenever we look at a matrix, this matrix has two equal rows. Then the determinant of if the determinant function exists, okay? Then the value of the determinant function is 0. No other choices. It's called the equal row. Okay? Questions? Any questions? Just exchange the ith row and the jth row. Exchange them. Theorem 4.1 from B. Called linearity on any row. Remember, we have axiom number 2. Axiom number says that we have linearity on the first row. But actually, this linearity is on any row. So it says that determinant of row 1, alpha, row I plus beta, row I prime, right? So if the ith row is the linear combination of two rows, then the value is equal to the alpha determinant R1, Ri, Rn plus beta determinant R1 up to Ri prime. Rn So we have linearity on any row, not just the first row. Why? Well, so the proof is here. The determinant 1 alpha Ri plus beta Ri prime. Rn. Now we decide to exchange the first row and the ith row. Once we exchange the first isotope, we have to change the sign. So we have minus determinant of alpha Ri plus beta Ri prime, the R1. So we exchange them. The Rn, we have minus sign. And so this is axiom number 3. Now, by the axiom number 2, because we have linearity on the first row, so we have determinant alpha I, 1 alpha n plus beta determinant I prime, 1, n. Okay, and now, so this is the axiom 2. Now by axiom 3, we exchange these two rows again. We exchange them. Then we have minus sign. So we minus alpha plus actually minus beta 1 I prime Rn. By axiom number 3 again. And finally, minus minus becomes plus. And we have that. Okay. So we have linearity on any row. Now property 4 by 1, 2. So this is the second axiom taken by the textbook. It's called the replacement. The operations. The determinant, when you apply, because when you apply the replacement operation, it's equivalent to you multiply this elementary matrix with the right? So that it means that you multiply the jth row with scalar alpha and add to the ith row, right? It's called replacement. And doing so will not change the determinant. Okay? So doing so, when you do the replacement operations, you will not change the value of the determinants. Okay. And the proof. And here, determinants. Okay. After that, after applying the replacement law operation, you have R1, and the I law becomes to Ri plus alpha Rj. Okay. So now the I law is a linear combination of two row vectors. So by the previous theorem, we have determinants of R1, Ri, Rj, Rn, plus alpha determinant R1, Rj, Rn by the linearity on any row, right? Linearity on any row. All right, and what is that? We have two identical rows. See here? So that the determinant value is equal to 0 by equal rows. Right? By equal rows, this is 0. So we have determinant I, J, N, and with that. Okay, so replacement law operation will not change the value of determinants. Okay, so what is it? All this one, even though it takes my time to, every time the matrix is so big, but just look at the rows in the matrix. Okay, we can deduce. Up to now, we have how many properties already? We have 4, I think so. 1, 2, 3. 3 properties, right? All can be deduced from the xm1 up to xm3. So we have more to do it. Okay. And they were quite natural. You will see that. Not very complicated. Okay. All right. So next Wednesday, we will have the first meeting examination. Okay, so it's closed book. As I described in my email, you can bring one sheet of paper. And you can write anything on both sides. For example, you can write all the theorems, right? You like. Or if possible, you can make the material visible into it. If you can, if you have the technology. All right. Anyway, so up to you. Okay. And then, so I ask you to, if you are able to do, just come to the TA office hour next Monday evening. Okay. You can ask questions from TA. Okay. Good luck.